Moving on to question 5 now, we have a question here on hypothesis testing, as more specifically, hypothesis testing with the Poisson distribution. Okay, so what we're told here is we're looking at information that's collected about accidents on a bypass, and it's found that the number of accidents per month is modelled with a Poisson distribution with mean 2.5. For the next part, it just tells us that this is changed to a series of 3-month periods that are recorded, and then it wants to test whether or not there was a change in the mean number of accidents per month. So for part A, it's just asking for us to state our hypotheses clearly and use a 5% level of significance to find the critical region for this test. So we've got to state the probability in each tail as well. So first off, let's write down the hypotheses here. So H0, well, this is for a 1 month period here, this 2.5. So if we want it for a 3-month period, all we've got to do is scale that up. So we're going to have to times it by 3. So 2.5 times by 3, well, that's going to be 7.5, right? Our lambda is going to be equal to 7.5. So let me just undo that because I need to put my lambda in. So let me just undo this. This is really bad. So it's going to be H0 lambda, so the mean, that's going to be equal to 7.5. Okay, my H1, so we've got to decide whether it's a 1-tailed or 2-tailed test. Well, because we're only deciding whether it's changed, it's not increased or decreased, it's going to be a 2-tailed, right? So we're not specifically looking whether it's increased or decreased, so it's 2-tailed. So that's lambda is not equal to 7.5. So a 2-tailed test. So I'm just writing this over here, this isn't part of my hypotheses here. So a 2-tailed test, so that means, because it's 5%, that's 2.5% at each tail. Each tail, okay? So what we're going to have to do first is we're going to have to consider the upper boundary's lower region, and then we need to consider the lower boundary and the upper region for that. So for this question, you need page 35 in the new Edexcel formula booklet for further maths. So further maths, formula booklet. Okay, so for the upper boundary lower region, so I'm going to call this UB upper boundary lower region. Well, what we're looking for here is the probability that X, so let me just write down my model first. So my model is that X is distributed with a Poisson with a mean of 7.5. So I'm looking for the probability that X is less than or equal to C1. Okay, that's just going to be my variable here, where this is close as possible to 2.5%. Close as possible. Close as possible to 2.5%. So how do I work out this C1 value? Well, all you've got to do is use the tables in the formula books. If you go to page 35, make sure you're looking across at lambda equals 7.5, because that's our model. And then you're going to go down and you want it to be as close to 2.5%. Well, the closest one there is when the probability for X is less than or equal to 2, okay? Because the value here for 2 is 0.0203. So therefore, my lower critical region, is X less than or equal to 2. Okay, so that's lower, believe it or not, lower critical region, and X must be less than or equal to 2. Now we can do the same with the the lower boundary upper region. This is a tongue twister between the two of them. So if I call it LBUR, what I need now is kind of the opposite. So I need the probability that X is greater than or equal to C2. And this again has to be as close as possible to 2.5%. Close as possible to 2.5%. Now, because this is X being greater than or equal to C2, what I'm going to have to consider is using the tables again. So again, page 35, and make sure you're going across with lambda equals 7.5. I need the region which is going to be closest to 2.5% again. Now remember, because this is greater than or equal, well, what you find is the closest value here is when it's 13, right? But because this is greater than, So if we just do it over here, remember when you calculate a probability, say x less than or equal to C2, this is going to be 1 minus the probability of x. So I just put a number in there, sorry. So I say that's 5. That'll be 1 minus the probability of x being less than or equal to 4, right? So, doing the same now, I get my value here of being 0.0216, okay? Now this is when it's 13. So my actual probability for this must be x being greater than or equal to 14, right? Because it's going to be 1 minus this. So therefore, this is going to be 1 minus this, or 1 minus probability of x being less than or equal to 13. So therefore, it must be 14 for my critical region. So if I just write this down over here, sorry, so upper critical region. So I'm kind of running out of room here. Hopefully, should just fit it on. Upper critical region is when x is greater than or equal to 14. And the probability for that is, like we said here, 0.0216. Okay, so them are the probabilities in each tail, and we found the critical regions for these tests. So that's all of part A. We don't need to do anything else. So let's just clear all that. For part B, just on 1 mark, we have to state the probability of a type 1 error using this test. So, type 1 error. Well, a type 1 error is when you reject when you shouldn't have. So, type 1 error is a reject when you shouldn't have. Okay, so the probability of doing that, well, that's just going to be simply my two critical regions from the last, my two critical probabilities, right, from the region. So if I add them two together, I'm going to get my probability of a type 1 error. So that's going to be, if I add them together, 0.0203 plus 0.0216. Add these together now, what do we get? Well, you're just going to get 0.0419. And there we go, so that's just a probability of a type 1 error using this test. Okay. Part C here. Well, what it's saying now is that the data from the series of 3-month periods are recorded for 2 years. And we have to find the probability that at least 2 of these 3-month periods give a significant result. So, how do we do this? Well, this is similar to the question 2 we did for this paper with the Poisson distribution again, where we're taking it in terms of a period now. Here, so we've got a 3-month period, this is recorded for 2 years, but it wants to know how many of these 3-month periods give a significant result. So we're not actually going to use the Poisson here. Hopefully you can spot that we're going to need the binomial now, okay, because we're modelling it in a number of different periods, right? So this is going to be y is distributed binomially. My sample here, well, how many 3-month periods go into 2 years? Well, that'll just be 8, because there's going to be 4 lots of 3-month periods in 1 year. That'll be 8. Now we want a significant result, sorry. So that'll be using the probability here, because this is where we get a significant result. So it's going to be 0.0419. So using this now, we need to work out the probability that at least 2 of these 3-month periods give a significant result. Well, that'll just simply be the probability that y, because we're using the model y, is greater than or equal to 2. This is my model for at least 2. Well, that's going to be 1 minus the probability that y is less than or equal to 1. And if you just plug this in on your calculator now, using the binomial distribution on the stats mode, you're going to get 0.0415. And there we have it. So that's the probability for C there. And then finally for D, we have to find the probability of a type 2 error. And it's modelled by a slightly different scenario, because after the work's completed, the actual mean is 2.1 per month. Okay, so I'm going to need a new distribution now. So if I clear this. So if it's 2.1 per month, and we're looking at a 3-month period, well, I'm going to have to scale that up by 3, right? I'm going to have to times it by 3. So my new distribution is y is distributed binomially with a mean of 6.3, okay? Because 2.1 times 3 is 6.3. Now, we need to use the critical regions that we already worked out in part A, because we're using the test in part A. Well, we worked out the probabilities here Well, when y is less than or equal to 2, and that would also be when probability of y is greater than or equal to 14. Okay. Well, using this information now, oh sorry, this is a Poisson, sorry, I don't know why I put B, that's a Poisson there. So now I've got my two probabilities here. Just using my calculator here, my Poisson distribution on my stats mode to get my two different probabilities here. So it's going to be 0.04984649317. Now I'm going to write all my digits down. Obviously you don't have to show these down individually on paper if you can just times them, but I'm going to show it just so I don't lose any degrees of accuracy here. This one will be 1 minus the probability of x being less than or equal to 13. So that's going to be 0.005485286. I'm just making sure I don't accidentally write this down incorrectly. Now, like we did in part B, we need to add these together, but because it's a type 2 error, we then do 1 minus the sum of these. So therefore, type 2 error, well, that's going to be equal to 1 minus the sum of these. So, what's the sum of these? That's going to be 1 minus the sum of these together, which will give me 0.05533178177. And then if you calculate that, you're just going to get 0.945. So 3 significant figures. And there we have it. So that's question 5 fully complete.